Alkanoic acids. Alkanoic acids contain an alkyl group combined with at least one carboxyl functional group, and that's this right over here, COOH. They are a subgroup of carboxylic acids. The carboxyl group consists of a carbonyl group and a hydroxyl group connected to the carbon in the carbonyl group. Alkanoic acids are represented by R-COOH, where R is an alkyl group. So what do we have here? Let's look at the ball and stick diagram. Here's CH3, and here's a C right over here. Here's a double bond to oxygen, and here's a single bond to the OH. And this is ethanoic acid. When a methyl group, that is CH3, we'll draw it down here, in an alkane, and here's your alkane, is replaced by a carboxyl group right over here, it becomes a monoprotic alkanoic acid. This alters the molecular formula of the original alkane by adding 2 oxygen atoms and subtracting 2 hydrogen atoms. So here's our general formula for an alkane, and we take away 2 hydrogens, so the 2n plus 2 becomes 2n, and then we add 2 oxygens. Effectively, 2 hydrogen atoms are replaced by 2 oxygen atoms. Here are the molecular formulas for the first 8 monoprotic alkanoic acids and the general formula for those acids. I think we said on the previous slide it's CnH2nO2, and here's the alkane version. So let's look at butane. We have C4H10. So to make the alkanoic acid, the carbon stays the same, but we subtract 2 hydrogen atoms. So 10 minus 2 is 8, and then we add 2 oxygen. This chart shows the condensed form for the first 8 monoprotic alkanoic acids with the carboxyl group clearly indicated at the end here. So we're just rewriting it. So our formula now, instead of CnH2nO2, we took one of the carbons out, put it over here, and what did we do? We took one of the hydrogens out. So we have to subtract 1, and there's the hydrogen, and then we still have our carboxyl group over here, which has the 2 O's in it. The condensed formulas can be shortened by replacing a string of N-CH2s with CH2 subscript N, as shown below. So we have a CH3 in front, then we have CH2, and we have a number of them here. And this would be still our carboxyl group at the end. And the general formula for this now would be CH3, and CH2, N minus 2 of them. We're just making it fit the formulas here. And here's the N over here. But then when we want the general formula, we need the N minus 2 because we have the CH3 in front. When a methyl group is replaced by a carboxyl group, the parent alkane becomes a monoprotic alkanoic acid. So to name it, you drop the E of the parent alkane and add oic acid to the name ending. Some of these acids also have common names. So here, for example, is methanoic acid, also known as formic acid. I think ants secrete that for defense. Ethanoic acid becomes acetic acid or vinegar. Propanoic acid becomes propionic acid, etc. Compounds containing 2 carboxylic acid groups are called diacids, and their names end with dioic acids. Compounds containing 3 carboxylic acid groups are called triacids or trioic acids. Many diacids and triacids have common names accepted by IUPAC. For example, oxalic acid is also known as ethane dioic acid. Malonic acid is also known as propane dioic acid. And then here's citric acid, which is just called citric acid. Oxalic and malonic acids are diacids. Citric acid is a triacid. And here you can see 1, 2, 3. Malonic is a diacid. Here's our 2 groups. And oxalic acid, where's our 2 groups here? 1, 2. A fatty acid is a long-chain monocarboxylic acid. The long chain can be saturated or unsaturated. They are more common in fats, and hence they're called fatty acids. The number of carbons can vary from 12 to 36. Omega-3 fatty acids from fish oil, lauric acid from coconut oil, and palm fruit are a few examples. They all have a long hydrocarbon chain here and the acid group at the end. Solubility. We're dealing with some properties of acids now. Due to the presence of the hydroxyl group and its hydrogen bonding with water, smaller carboxylic acids are polar and soluble in water. As the length of the carbon chain increases, the polarity decreases, and so does the solubility. Lower members have distinct odors or pungent smells. Higher members have an unpleasant smell. The boiling point of carboxylic acids increases with molecular weight. The acids with even number of carbon atoms have a higher boiling point than the odd number carbon atoms immediately below or above. This is attributed to the better fit in the crystal structure for the even-numbered ones. The boiling point of acetic, that is ethanoic acid, is higher than ethanol due to its stronger hydrogen bonding. Carboxylic acids are weakly acidic in nature. They can donate the hydrogen atom of their OH group and form salts with bases. Their pH ranges from 3 to 5 on the pH scale. They will change blue litmus paper to a red-orange color. Their salts and carboxylates are ionic and more water-soluble. Carboxylate ions play vital roles in controlling physiological pH. Alkanoic acids have a wide range of uses. Formic, otherwise known as methanoic acid, is used in coagulating rubber, dyeing wool and fabrics, tanning of leather, and preserving fruit juices. Formic acid is also present in some ants, and we mentioned that a few slides ago, and causes burning and itching when they sting. Acetic acid, used for making aspirin. Ethanoic acid, otherwise known as vinegar, is used in the food industry as a preservative and additive. And finally, citric acid from citrus fruits and berries is an antioxidant and provides vitamin C. Here's a nice picture of some various acids. Okay, we talked about acetic and vinegar, formic acid with ants, malic acid, well, that would come from apples, citric acid, oxalic acid, that's a tomato, tartaric acid, blueberries, and then lactic acid in milk. I wonder if that's what causes lactose intolerance in some people. Interesting. This picture is showing that multiple acids can be present in each fruit. So here we have citric acid in these various fruits. Okay, malic acid would be over here, and tartaric acid is here. And let's see, grapes have tartaric acid, and they also have malic acid. Fatty acids are present in these foods. Olives, nuts, I guess that's butter, salmon, eggs, avocado, etc. Long-chain fatty acids like lauric acid, coconut oil, and omega-3 acids are used as food supplements. Carboxylic acid derivatives have a wide range of uses in synthetic chemistry, making esters, amides, halides, etc. So omega fats, I think they generally tell you those are pretty good for you, especially the omega-3 that comes from fish oil. Then here's omega-6, and here's omega-9. And this is like turkey fat, goose fat. That doesn't sound very healthy. And then here's your saturated fats over here. Lactic acid, and here's the formal name, and pyruvic acid play vital roles in our body's physiological processes. Lactic acid is produced during anaerobic respiration. That happens when there's not enough oxygen for normal respiration. It is a mild toxin, and buildup of this lactic acid causes your muscles to ache. So, summarizing here, lactic acid buildup is what causes muscle ache and pain. It is then carried back to the liver, where it can be converted back to pyruvate, and then your muscles will feel better.